Again, welcome to Mathematical Structure for Computer Science. This is CS 113 course, also known as Discrete Mathematics. These lectures will cover Chapter 10, Section 5 of our course textbook. And the topic is Euler and Hamiltonian graphs. So our main objective is to go through the Europa Paths and also Europa Circuits and Hamilton Paths and also Hermitian Circuits. Then we shall discuss some applications of both Euler and Hermitian circuits. So we start with the Euler paths and circuits. An example given here is a town that is divided by 4 sections and is connected by a bridge. The town is divided by 4 sections with a river, as we can see in the diagram here. We have the rivers, that's the blue lines here are the bridges. We have 4 sections of the town, A, B, C, D. And the rivers are where we have the bridges connect. So the concept of Euler path or circuit is that, is it possible that we can start from, let's say, bridge 1 and visit all the towns by also visiting all the bridges only once and then come back to the starting bridge? Actually, the model of the town and bridges is what is given to us here as a graph. So we have a graph with 4 ridges or sections of the towns, which is A, B, C, D. The bridge are the edges that connect the vertices. So now our question is that if I'm at vertex C, can I visit all the edges once and come back to vertex C again? So Euler proved this, that it's impossible. And that was one of the first theorem ever proved in graph theory. So here we say that a town of Königsberg, Prussia, now known as Kaliningrad, Russia, was divided into 4 sections by the branches of the Brechel River. In the 18th century, 7 bridges connected these regions. So we have 7 bridges or 7 edges connected the 4 vertices, which are the towns. Now, people wondered whether it was possible to follow a path that crosses each bridge exactly once. So now we want to follow a path that crosses each bridge exactly once and will return back to the starting point. And according to the Swiss mathematician Leonhard Euler, it proved that no such path exists. So this result is often considered the first theorem ever proved in graph theory. So the graph we have here, there's no path that we can start from C and then come back to C by going through each edge once, all the edges once. Yeah, if we skip some of the edges, we can. For example, I can go from C to A to B, B to D, D to C. But remember, I skipped 2 edges here, or I skipped 2 bridges. But here we want to go through all the bridges. So that path does not exist. So the definition of Euler path and circuit is given here. And here we say that an Euler circuit in a graph G is a simple circuit containing every edge of G. And also the Euler path in G is a simple path containing every edges of G. So example given here, they say which of the undirected graph G1, G2, and G3 has a Euler circuit? If not, has a Euler path. A, we can see by observing A, I can see that there's a Euler circuit here. because I can start from A and I'll end up at A and I'll visit all the edges. So from A, we go to E, C, D, E, B, and back to A. So we say graph G1 has a Euler circuit, example, A, E, C, D, E, B, A. But as can easily be verified by inspection, G2 and G3 has no Euler circuit. So let's say if I start from A, I can go A, D, C, B, and A, but I didn't go anywhere in the middle. So I'll start A, D, E, then A, B. But since I go A, B, and I already visited all the edges on my left side here, there's no way I can come back to A without going through the same edge twice. And even if I start from C, the same concept. I can go C, B, E, then C. But remember, if I go D and A, I have to, since I started from C or B, I have to end up there. So I'll still visit twice. The same thing applies to G3. But with G3, we can say that we have a Europa Path, which will be A, C, D, E, then we go to B, then we go to D, then we go to A, then we go to B. This is a path, this is not a circuit. The reason why this is a circuit means if I start from A, I have to end at A. A path means I will go through all the edges once, but where I start, I don't end it there. G2 doesn't have a circuit and doesn't have a path. There's no way I can even go through all these edges and be able to visit all the vertices only once. I don't care where we end it. We can end anywhere, B, D, C, we can end at anywhere. That will give us a path. Circuit will give us where we start is where we end. So that's what the definition said. An Euler circuit in a graph G is a simple set containing every edge of G. And also an Euler path in a G is a simple path containing every edges of G also. But the difference between the two is that circuit is like a close connection. So when I start from A, I will end at A, which means I close everything. But the path, I can start from A and I can end up at D or C. But as far as I visit all the edges, then it's a path. So hopefully this example gave us the difference or the meaning of Euler circuit and also Euler path. Euler circuit will be like a closed diagram, or in this case, we can say a closed graph connection diagram. I start from A, I visit all the edges, and I'll end at A. That's a diagram, Euler circuit. Here, I can't do that. But in G3, I can start from A and visit all the edges, but I'm going to end at B instead of A. If I end at A, then I have a circuit, but I can, in this case, I end at B. Or even I can end anywhere. Yeah, it doesn't matter, anywhere. If where I start, if I end it there and I visit all the edges, it's a circuit. Where I start and I visit all the edges, but I end at different place, not at the starting place, it's a path. So there are some few necessary conditions for Euler circuits and path. So here we say an Euler circuit, again, this is a circuit. So it begins with a vertex A and continues with an edge incident with A, say from AB. The edge AB contributes 1 to degree A. Now, each time the circuit passes through a vertex, is going to contribute 2 to the vertex degree. And finally, the circuit terminates where it started. And that's a Euler circuit, contributing 1 more to degree A. Therefore, degree here must be even. What we mean the starting, we can even see from this diagram. We said this is a Euler circuit. We start from A and we end at A. So we can see that A is an even, the edge is 2. But here you can see that A is 3. That's why we couldn't start and end at A. So we conclude that the degree of every other vertex must also be even. This is for the Euler circuits. Now, by the same reason, we see that the initial vertex and also the final vertex of a Europa path, not a circuit. A circuit is always even, but Europa path have odd degree, so that is the starting and ending. Why every other vertex has even degree? So let's check the G3. We start at A and we end at B. So we can see that A have 3, which is odd. The degree of B also have 3, which is odd. But E have 2, D have 4, C have 2. So that's the condition here. The Europa path, the starting and the ending vertex will have a odd degree. It can be 3, 5, 7, odd degree. But the remaining vertex will have an even degree. Otherwise, the path, we cannot visit all the edges to make a path. That's why when we go back, the G2, we don't have any starting for 3, ending for 3. So like for example, A is 3 odd, B is 3 odd, but also look, C is 3. Only the starting, only 2 have to be odd, then the rest is even. But here we have odd for 1, 2, 3, 4. They are all odd. And also E is 1, 2, 3, 4. So E is even, but A, B, C, D, they are all odd. With the Euler path, the starting should be odd degree, and ending also should be odd degree. Then the rest should be even. So if I'm going to look for a question is given and this graph is given, and they say I should look for the Euler path, I'm not going to start with E. It's just wasting my time. Or maybe I'll say just a try and error. But because even is 2, always look for the odds. And even you can count how many odds degree you have. You shouldn't have more than 2. Otherwise, we can't get the Euler path. So that's these conditions is very important. We should consider these conditions when we are looking for Euler circuits and path. So again, by the same reason, we see that the initial vertex and the final vertex of an Euler path have a odd degree, while every other vertex has even degree. So a graph with an Euler path has exactly 2 vertices of odd degree. So if a graph is given and they say we should look for the Euler path, we should check how many odd degrees we have. It should be 2 and the rest should be even. With regard to Euler circuit, we say that Euler circuit, we begin with vertex A, continue with an edge incident with A, say A and B, then we contribute. But with a Euler circuit, looking at this diagram, the starting should be even. Euler path starting and ending should be odd degree. But Euler circuit, the starting and ending is the same vertex because we go around and come back to the same. So you have to be even. And there's a condition somewhere here. Finally, the circuit terminates where it started, contributing 1 to degree. Therefore, the degree A, the starting, must be even. Then we conclude that the degree of every other vertex must also be even. That's for the circuit. But for path, the starting and the ending should be odd, and the rest should be even. But circuits, starting and end is the same point have to be even, and the rest also have to be even. And that's the degree of vertex, even. So we have sufficient condition for Euler circuit and path. Now suppose that G is connected multigraph with and the connection multigraph with the vector n 2 greater than or equal to 2 vertices. So here we have a multigraph that have 2 or more vertices, and also all of even degree. Now we are saying that suppose G is connected multigraph with more than 2 or more vertices. This is greater than or equal, so 2 or more vertices, all of even degree. Let us remember we said that Euler circuit, all the vertex must have even degree. So we said that let SO equal to A be a vertex of even degree. Choose an edge, SO and S1. Incident means the two vertices have to be adjacent, have to be connected by the same edge with A, and proceed to build a simple path x0, x1, s1, s2, sn, n1, so s3, 4, 5, and 6, so by adding edges one by one until another edge cannot be added. So this is a good example here. We illustrate this idea in the graph G here. We begin at A and choose the edges A, F, F, C, C, B, B, C. So we begin at A, we get the edge AF, then FC, then BC, then come back to BA. So this is again a circuit. You can see that all the vectors have even degree of each one, 2, 2, 2 even degree. Now we say that the path begins with A, at A with an edge of the form AX. We show that it must terminate at A with an edge of the form YA. Since each vertex has an even degree, there must be an even number of edges incident with this vertex. Hence, every time we enter a vertex other than A, we can leave it. Therefore, the path can only end at A. Now, if all of the edges have been used, an Euler circuit has been constructed. Otherwise, we should consider a subgraph H obtained from G by deleting the edges already used. So that's the sample given here. And this, the continuation. Now we say because G is connected, H must have at least one vertex in common with the circuit that has been deleted. And the common is the C. So the C connects G and H. So in this example, the vertex is C. Now every vertex in H must be even degree because all the vertices in G have even degree, and that's right, even degree. And for each vertex, the pairs of edge incident with this vertex have been deleted. Now, beginning with the shared vertex, we should construct a path ending in the same vertex as was done before, then splice this new circuit into the original circuit. So in the example we have here, we end up with AF, then we have C, then we have E, then we have C, then we have B, and then A. So we have to continue this process until all the edges have been used. This will produce an Euler circuit. Since every edge is included, no edge is included more than once. So the theorem here is that a connected multigraph with at least two vertices has an Euler circuit if and only if each of its vertices has an even degree. So all the vertices must have an even degree, and it has also a Euler path if and only if it has exactly two vertices of odd degree. So that's the main foundation of Euler circuit and Euler path, as we saw in the first example. A Euler circuit, I will look and make sure all the vertices in the circuit have an even degree before I even check. If any circuit have an odd degree, any of the vertices has a odd degree, then I know there's no Euler circuit. But it's possible there will be a Euler path. So with Euler path, we still have to check that the beginning, the starting and the ending point should be odd. So with Euler path, only two vertices will have a odd degree, the starting and the end. So two of the vertices in the multigraph model of the Königsberg bridge problem have odd degree. Hence, there's no Euler circuit. So that's why this is the proof that Euler gave to us. We can see here a Euler circuit means when I start from C, I will go through all the edges and I'll end at C. But in order to do that, the theory said all the vertices must have all the vertices. In this case, all the four sections, A, B, C, D of the town regions, the four regions, must be even. But we have odd here. C is odd, and also D is odd. So that's impossible. So that's what we mentioned here. Two of the vertices in multigraph model of Königsberg bridge problem have the odd degree. Actually, that's the diagram here. And I went back. So this is the diagram. Hence, there's no Euler circuit. We can't start C and end at C. Or we can start at A and end at A by visiting all the edges once. Because we have some odd. D is odd. A is even or odd. So now, let's say this example here. We have a Euler circuit and path example. We have G1. Let's check if G1 is a circuit. If it's not a circuit, then we are going to check if it's a path. So first I'll look at how many degree. I have two here, but I have three here, so it's not a circuit. It's possible it can be a path. Let me make sure we have only, so we have only two odd degree, B and D. So there will be a path. So here we say G contains exactly two vertices of odd degree, that's B and D. Hence, it has a Euler path. And the path will be D. We have to be careful because we have to visit all the edges, but we are not going to end at D. So we start with D, A, B, then C, then D, then B. So you can see that we start at D, but we end at B. But we were able to visit all the edges once. We visit all the edges once. Now let's look at B. The G2, we have two, one, no, so we don't have no circuit. First, we don't have no circuit because we have at least one, I can see one odd degree. But let's see if we have more than two odd degree. We have one odd degree here. B also is a odd degree. C, oh, okay, C also is odd degree. So we have more than, since we have more than two odd degree and we have some even degree, it means we don't have no Euler circuit and also no Euler path. So let's see the solution. G2 has exactly two vertices of odd degree, B and D, hence it has a, no, maybe I calculate something wrong. I said C have a, okay, sorry, I didn't go both sides. I count only one. So C is 1, 2, 3. We have C to B and also we have C to D. So it's both sides. So it's 4. I thought it's 3. So we only have, and also this is 1, 2, 3, but to the right is 4. It's 4. So only B 1, 2, 3, and only D 1, 2, 3. E is 2, F is 4, 1, 2, 3, 4. G, I thought it's 3, but to my right also, we have G to F, G to A, G to C, G to B, so 4. So the rest other have, all the rest are even. So there's a path. So we have to be careful where we start from. Let's say we start from B, we can go B, A, G, then we go to F, then we go to E, then we go to D, then we go to C, then we go to G, then we go to B, then we go to C, then we didn't go the up, so we go to F, then we go to D. This is where we're going to end it. So you can see that we start with B again and we end at D. Again, the reason why we know there's a path here, because we have exactly 2 odds, which is D, 1, 2, 3. And the odds is the place that we are going to end. So for example, if I have this and I know that my B is an odd degree, my D is an odd degree, and I'm going to start with C, I'm wasting my time. We can't get a path starting from C. Either we get a path starting from B or D, so we may try one of these, B and D. So now let's look at the G3. First, we look at the vertices and the degree 1, 2, 3 for F, 1, 2, 3 for E, 1, 2, 3 for D. So here we have 6 vertices that have a whole degree. So it does not have either. A circuit means all have to be even. A path means only 2 have to be odd. The starting and ending vertex must be odd. So G3, we don't have any path and we don't have any circuit. So applications of Euler paths and circuits, there are so many applications. Here we say Euler paths and circuit can be used to solve many practical problems, such as finding a path or a circuit that traverses each. Example would be a street in a neighborhood, or road in a transportation network, or connections in a utility grid. We can trace the links, or the link in a communication network, like websites, etc. Other applications are found in the layout of circuits, network multicasting, molecular biology, where Euler paths are used in the sequencing of DNA. So next we talk about Hermitian paths and circuits. So the definition is a simple path in a graph G that passes through every vertex exactly once is called Hermitian path. So it's the same concept as Euler, but the method of going through is slightly different. So a simple path in a graph G that passes through every exactly vertex once is called Hermitian path. And a simple circuit in a graph G that passes through every vertex exactly once is called Hermitian circuit. So a simple path can be S0, 1 up to Sn minus 1 to Sn. In a graph G with vertex and edges is called a Hermetic path of V from SO to Sn. And here we make sure Si is not equal to Sj. So I should be greater than or equal to 0, but less than J, which is less than or equal to N. Now let's see an example. Which of these simple graphs has a Hermitian circuit, or if not, have a Hermitian path? The solution says G1 has a Hermitian circuit. So this concept is the same as a Euler circuit. Here we start from actually the same question. We start from A, B, Then we have AB. Then we have C, D, E, A. So G1 has a Hermitian circuit, which is again AB, AB, C, D, then E, A. Now G2 does not have a Hermetic circuit. Why? But does have a Hermetic path. The Hermetic path will be ABCD, which is AB, ABCD. Hermetic circuit is for G1 is AB, C, D, E, A. Now G3 does not have Hermetic circuit or Hermetic path. So there's a necessary condition for Hermetic circuits. Here we say, unlike for an Euler circuit, no simple, necessary, and sufficient conditions are known for existence of Hermetic circuit. We know Europa Path, at least two vertices should be odd. Only two, not less than two, because the starting and ending two. Then with the circuit, all the vertices must be even. But with Hamilton, there's no a simple condition. But however, there are some useful necessary conditions we describe. Two of them, one is the Dirac's theorem. Now, Dirac's theorem said if we have a graph G, and it's a simple graph with with three or more vertices, such that the degree of every vertex in G is greater than or equal to n divided by 2. Then G has a Hamilton circuit. What this means is that if I have a vertex, I have a graph, and there's 4 vertices, and then we have 4 divided by 2, that will give me 2. So we say the degree of every vertex in G is 2. Then we have a Hermetic circuit. Or if it's 8, 8 divided by 2 is 4. If all the degree of the vertices is 4, then we have a Hermetic circuit. Also, Orion's theorem said that if G is a simple graph with n equal or greater than 3 vertices, such that degree of U plus degree of V is greater than or equal to n for every pair of non-adjacent vertices, then we have a Hermetic circuit. Non-adjacent vertices means if A is connected to B, B connected to C, A and C will be non-adjacent. And that's the condition we use. So what are the applications of Hermetic paths and circuits? Example here, we say application that asks for a path or a circuit that visits each intersection of a city, each place pipelines intersect in a utility grid, or each node in a communication network exactly once can be solved by finding Hermetic path in appropriate graph. And also our famous traveling self-spacing problem. This problem is solved a lot in data structure course, finding the shortest path. So travel self-spacing problem asks for the shortest route a travel salesperson should take to visit a set of cities. This problem reduced to finding Hermetic circuit such that the total sum of the weights of each edge is as small as possible. We are going to discuss this in our next section, how to find the shortest path in a graph. Also, a family of a binary code, such as gray code, which minimize the effect of transmission errors, and also corresponding to Hermetic circuit in the N cube. We're going to discuss this also. So let's see some example here. Here they say we should determine whether the given path has an Euler circuit. If it has a Euler circuit, then we should construct such circuit when one exists. If no Euler circuit exists, then we should check if it has a Europa path, then we should construct the Europa path. So first, we are going to look if there's a Euler circuit, which means all the vertices should be even. When we look, A is 2, B is 4, E is 4, F is 4, C is 2, I is 2, H is 1, 2, 3, 4. So we can see that all the vertices, the degree is even number, either 2 or 4. So there should be a circuit here. There's a circuit. Now, they say we should draw the circuit. So let's start, we can start from A and we have to end at A if we start. So we start with A, we go to B, then we go to E. Sorry, it's better we go to C. So A, B, C, then F, I, then H, then G, then D. After D, then we can go the inner now, because we have to end up at A. We haven't go through A, B yet. So from D, we can go to E. Then from E, we can go to H. From H, we can go to F. From F, remember, we haven't go to EF, so we go back to E. Then we go up now, we go to B, then we go our last D, then come back to A. So we visit the whole edges once. We start from A and we end at A. So again, to be AB, so we go AB already. So we have to end at that AD. So AB, then we have C, then we have F, then we have I, then we have H, then we have G, then we come back to D. Now we have to visit the inner. So we went to E, then we went to H, then we went to F, then we went to F to E, then we went to B, then we come back to D, then the last is A. So that would be our circuit. The second question said, determine whether the given graph has an Euler circuit, then we should construct such circuit when one exists. If not, we should check if we have a Euler path, and then we construct it. So first, let's say there's a circuit, we need F is 3, 1, 2, 3, so we stop. Euler circuit means all the degree of the vertices must be 2, 4, 6, must be even number. Here we have 3, so there's no Euler circuit. Now let's see if we have only 3 degrees for 2. That's only 2 vertices have 3 or odd number. So F is 1, A is even, B is even 1, 2, 3, 4. D is even 1, 2, 3, 4. C is 1, 2, 3. So C and F. Okay, so we have a path. E is even, is 4. So only F and C have a odd. So here we say the graph has no Euler circuit since the degree of vertex C for 1 is odd. But there's a path between the 2 vertices of odd degree. Because why? The C also, C and F is odd, 2 of them. So we need to start from F and we have to end at C. Or if we start from C, we have to end at F, because those are the only 2 odd degree of vertex. So we start with the F, we go through A, then we go through B, then we go through C, then we go through D, D take us to E, E take us to F, and then F take us to B, B take us to D, D will take us to A, then A will go all the way to E. So we finish. And the last from E, we go to C. C is a 3 odd, F is odd. So that would be our path. Then problem 3 said, in exercise 22, let's assume this is 22. Again, this is a question from our course textbook. We have to answer the question from 18 to 23, but I chose only 22. So we should determine whether the directed graph here shown has a Euler circuit. If it has, we should construct it. If not, we should check if you have a Europa path. If it has, we should construct a Europa path. So here, this directed graph satisfies the conditions of exercise 17, but not that of exercise 16. Therefore, there's no Euler circuit. Euler circuit, we gave the condition. So let's look at A. Everything have to be even, but you look at A, we have 1, 2, 3, 4, which is good. B, we start from here 1, 2, 3, 4, 5, 6, 7. So I will stop and let's cross check and make sure B is odd. 1, 2, 3. Oh, sorry, this is a directed graph. A directed graph. So we only count the arrows that is moving out. So here we have 1 and 2 for A, 1 and 2. And the other one is going in. And here we have 1 and 2 and 3. And with 3 and we have 4. And here we have 1, 2, and 3. So here we know that there's no Euler circuit because of the condition. But the Euler path must go from C to B. So which means C was a odd as we count it. We have 1, 2, and 3. You can see that 3 arrows is going away from C, so it's a odd. And also B is a odd. B, we have 1, 2, and also 3. Only three arrows is going out. So the rest will be 4. Let's see, let's try, the rest will be even. So let's try any one. Let's cross check E and see if it's even. We are here even. E, we have 1 going out and 2 going out also. The rest is going in, so it's even. F, we have 1 going out and 2 going out and 3 and 4. So the only thing is C and B. So we start with the C. So we move from C to E, we have 1 arrow. Then E, we can go to B, only B we can go to B or F. So let's go to B. Then we can go to D. Then from D, we can go to C. Again, we're following the arrow. Then C, we have on one edge also. B, we have to visit all the edges with the arrow going out. So now we are in B. From B, we can also go to F. Then from F, we can go to D. Then from D, we can go to E. Then from E, we can go to F. Then from F, we can go to A. Then from A, we can go to B. Then from B, we can go to C. Then C, we end it and we go to B. So from C, so it's like a loop, go C, then B. So that will be our Eulerian path. And next question says, for which values of n do this graph have an Euler circuit? Kn, Cn, Wn, Qn. So here we said that the degree of vertices n minus 1 are even if and only if n is odd. So here we have Kn. The condition is saying that the degree of the vertices n-1 are even if and only if n is odd. Therefore, there's an Euler circuit if and only if n is odd, and they're greater than 1, of course. And if we have Cn also the same thing, we can say that for all n, we saw this condition. If n is equal to 3 or more, clearly Cn as a Euler circuit. Then Wn, we say since the degree of the vertices around the rim are all odd, no wheel has an Euler circuit. And the degree of the vertices are all n. Therefore, there is a Euler circuit if and only if n is even on this. So this will be the conclusion of our lectures. And hopefully, if you have any question, again, send an email, or again, you can reach me on my contact number. And I wish everybody the best. Our last lectures on graph will be how to find the shortest path in a graph. And we are going to use the weighted graph. A weighted graph means there is the edge has some value assigned. So let's say we have a graph of a city, and we say, okay, from Brooklyn to Bronx, the edge is 50. The 50 means from Bronx is a vertex, Brooklyn is a vertex. We have a edge with 50, which means the distance from Bronx to Brooklyn is 50 meters or 50 miles, etc. So that's the next section we're going to cover. So again, wish everybody the best, and thank you.